Him about it. He's been a good friend of mine for quite a while. Mert introduced me to him way back in I think 2000 at one of the FDIM conferences, and when Dave used to go to those, he quit going to them because he had such a backlog of rigs, and he said it wasn't fair to go to those and sell it to the new people when he had a backlog this long that he couldn't get to at home. So he thought that wasn't fair, so he quit coming to him. But anyway, we've corresponded a lot through the years. Now, I don't know if you know Dave Benson. He used to be NN1G. Now he's K1SWL. He's a real famous QRPer. Way back in the NorCal days, he used to have lots of articles. If you look back through the old NorCal, back in the 80s and 90s, he was one of the real prolific writers. And he was one of the first, I think in the first batch of Hall of Famers, when Wes Hayward and Doug DuMont, a bunch of these guys got in. Dave was another one of these who was right there, you know, with those guys, because he is very well known and a very prolific, incredible designer. Anyway, we've become friends and we've corresponded a lot over the years. And so I started asking him about the rig, and I found out, he said, well, I don't know if you saw my webpage, but just yesterday I announced I'm no longer going to be selling any kits, virtually any kits. He got out of the business. He's going to sell his Rocklight and a couple others that'll go on forever. But he got tired of it. He got tired of people calling up and saying, I got this $100 radio from you and I'm going to send it to you and I want you to fix it for me. And he says, I'm not going to keep doing it. He said, people are willing to spend some money when they got a $500 or $1,000, $2,000 rig. They're willing to spend something for fixing it up. But for a little one, they don't want to spend anything and they expect you to fix it up for them. He says, I'm out of that. I'm not doing that anymore. So I actually found this one on the internet. One of the guys was selling one and it was busted. That's one of the reasons they were selling it. But I was able to fix it up and it does work. I got the thing working. I had another one also that is still a basket case. And I told Dave I'm going to send it to him and see if you could fix it up for me. He said, I'd love to fix it for you. I've got two tools, a sledgehammer and a shotgun. Which would you like? Dave's a real quiet guy, by the way. That's why he moved to New Hampshire, and he lives out there. He just built a house of his own way out in the woods. And but he used to work for the same company that I did years ago, Univac. Back in those days, he worked for a different branch. But we've had lots of correspondence and things like that. But anyway, he's been a good friend. Once we told him we were thinking about an AM project, kind of like his retro for our club project, he kind of got excited. He said, I'm not making that anymore. But he said it had some real deficiencies. It had a couple of real problems in it. But I tell you what, if you want to do it as a club, I'd be glad to throw it over the wall to you and show you what to do to fix it up, as long as I don't have to support it. So I thought, well, that's a good idea. He told me two major deficiencies. One was an AM detector, and we'll look at that in a little bit. And the other was the transmitter. The modulation transformer was saturating, so it wasn't getting full modulation. So he was getting weak signals out of it. But they have people using those all up and down the East Coast. From many, many states away. It was at a couple of watts. And they worked, okay? And he had a lot of fun with them. But he just said, time has come and I'm not going to sell them anymore. So Mert and I were looking at ideas and how to fix it up. And we did I ran some ideas that I'll show you in a second here for the receiver modification. And he, more or less gave the buy-off on saying, yeah, that's the way to go. That's what you want to do. And so we started taking off and working on designs and started prototyping things. Now, the other part of it is the retro is single frequency, okay? There's a 40-meter one and an 80-meter one, but basically it's one frequency. It's crystal controlled. You can switch between a couple crystals, but basically one frequency. And we thought it would be kind of nice to be able to change the frequency a little bit, and since I've got a signal generator here, we thought we could feed that into it, and we could vary it around a little bit. Within the AM windows, there are certain band ranges that they say are kind of good for AM that they want to kind of keep us in. Now, one of the things that we talked about is, why not go right to a sideband rig? Okay, well, first of all, double sideband. There's quite a few real simple ones out there. You make two double sideband rigs, they can't talk to each other. Figure that one out. You can talk double sideband to a sideband maybe to a double sideband, but double sideband to double sideband doesn't work. And talking to Dave about that, he said, yeah, because the phasing's screwed up. I had to wrap my head around that a little bit as to why that didn't work. But so AM, why not AM? Okay, the reason we don't do AM in general, why they do sideband, is because of power. Okay, it's easier. You try to strip off as much things when you're transmitting as you can, so you don't waste power transmitting the parts that you don't need. And so you get down to a single sideband, and that's the most efficient out of the voice. Well, we're having to put a double sideband, two of the sidebands, plus a carrier, and that's wasting some power. But there's something about an AM signal. I don't know how guys have been on AM before, But there's something about tuning across an AM signal that's kind of like, ah. Well, you know, tuning across an AM band in the radio, okay? And you don't go, no, it's there. You tune from one station to another. It's quiet. It's peaceful. It's sometimes they fade out. Sometimes, but it's nice, peaceful, quiet, and that's what it is on the. That's what we grew up doing. You could almost hear the clock ticking in the background because it was nice and crystal clear, and there was a beautiful fidelity. And that's what we can do with AM. Okay, we're not going to run a huge amount of power. We're going to run a couple watts, but that's going to be enough to be able to talk around the Twin Cities. And you can put an amplifier on it if you want to talk a little further. It's not too hard. Not too hard to put an amplifier. So basically, that's where we're coming from, and so we got some ideas here. I'm going to pass around the Retro 75 here. First of all, you can take a look at what that looks like, and then the next thing is a building block for it. I'll pass this around too. This is the SI 570 board that I'm actually selling this as a kit through Kanga. By the way, I'm not doing a sales pitch here, but this was the little project that was in QEX here about a year ago. The cover picture actually, so you can see how that works, and we're going to have, I'm making a simplified version of this, okay, for our rig. This one has a real small pick in it, and I had to shoehorn like crazy to get the code in there, and there's no room for any modifications, and for reasons I'll get to in a second, I had to make some modifications, and I couldn't get them in here, so I'm going to a larger pick, a better pick. It's a couple dollars more, but it's going to be a platform that I'll be able to use for all kinds of things. But basically it's this board with a couple additions on it. It doesn't have a daughter board anymore. It'll be built right on it, and so on. But this is a simplified version. You can play with it here and at least try it. So I'm going to go from there to a couple pictures now. Let me back up. When I went to this different resolution on the screen, all my icons got all spread out. I had them all sitting in a nice little row here. But I'm going to try to. Really good. Well, okay, we'll start out with, here's my basic design. This is the left side of it. And, well, I'll give you the whole thing to begin with. Okay, so what this is most of this is right from the Retro, okay, the Retro receiver. Except there's a modification out here that I'll show you. So it has a low-pass filter coming in up here, and then there's this is for transmit receive. But basically, Dave liked to go to these couple of transformers like this, of this type, with it makes a resonant circuit out here, and it tunes right into an SA612, NE602, all those kind of, real simple little mixer. Okay, and there's limitations of the NE602. I like diode ring mixers better in a lot of ways. But they don't have any conversion loss. They actually have a little gain, and they're real simple. And Dave really loves the SA602. Virtually all of his rigs have them. Good share of the Ellercraft rigs also have an NE602 for a mixer in them because they're nice and simple. Now this part down here is where my little signal generator will come in. This is just some simple little circuitry to beef the signal up a little bit into two flip-flops to divide by 4. I can't quite go low enough to get into the 80 and 40 meter bands directly, 7 megahertz and 3 megahertz. So I can get out to 10, okay, so I'm going to divide it down. But you won't even see it once I get the circuitry in there and change the dialing mechanism. You won't even know it, and you'll just, you'll be able to tune right to it. So after coming into, the antenna comes in through the low-pass filter, and the signal generator comes in through this divider, and they mix, okay? And they mix together and come out to an IF frequency, and you can't see it here. It's set to 11 megahertz. And I'll show you why. Here's a bigger picture of the left side of it, and those are the rigs. So they mix together and come out at 11 megahertz. Now, we're going to go just a little step back again. I want to talk about a couple of different kinds of signals and why we're doing it this way. First of all, without trying to make it sound too simple, I want to start some of the very basics, okay? When you start with a carrier like this, okay? Now, what is CW, okay? Let's start when, this is, by the way, at a time base, okay? This is time and this is voltage or whatever, or signal strength. When you put on a carrier at a certain frequency, let's say 7 megahertz to make it simple, okay? you have a carrier going full bore, okay? As long as you key it on, you put on the transmitter, it's going up and down. If you're doing CW, it just means you turn this whole thing on, and then you turn it off, and then you turn it on again, okay? There's CW. Now, what happens, if you look at this thing, you have to look at it in two different hats. This is on a time base. If you looked at an oscilloscope, this is what you'd see. If you looked at it on a spectrum analyzer, what would you see? Okay, once again, this is an amplitude. What would you see?
Very narrow pip.
You'd see one line. Assuming there's no phase noise, now line tech and ideal. Okay, one line, and this is your frequency. Okay. Now, the next stage is what would an amplitude modulation look like? Well, all we're going to be doing is just taking, instead of staying at one amplitude here, we're just going to be working on a transfer that will show you how to change this. So we're going to be going up and down here, and ideally it'll come down to here.
Doubles those above too.
Yeah, we'll come like this, right? You can come and drop, but basically we're going to be coming like this. So it's just the height, the strength of the signal is going to be modulated. Okay, instead of going full bore all the time, it's going to change it up and down by going through a transformer and circuitry. So now, okay, how fast is it going up and down? Say it was going up and down at 1 kHz. We should talk about cycles instead. Shouldn't we get back to AM? 1 kilocycles?
Cycles per second.
Yeah, right. This is 7 megacycles. Anyway, and so if you're going up and down at 1 kilohertz, okay, and this is 7 megahertz, what would you see out here in the spectrum analyzer?
Very wide pip. You'd see 2 lobes and a carrier.
You'd see one here, you'd see one here, and you'd see one here. This is too far apart, but so if this was 7 megahertz, okay, and this is 1 kilohertz, it'd be 7 plus 1, okay. You'd see the plus and the minus, okay. You see them added and subtracted, okay. Now, what happens when that's if you just put one tone out there, 1 kilohertz, right? But if you're actually putting voice on there, what's going to happen? It's going to broaden it out a little bit, right? It's going to mean these things are a little broader, so you actually have a little sideband like this. That's what an AM signal is going to look like. It's going to have 2 sidebands. You know, it's broad, based on we don't talk in one tone all the time. We talk in many tones, right, up and down, and that's why you're going to have a little broader here, okay? And so basically, AM is going to transmit both of these sidebands plus a carrier, okay? When you run double sideband, you just do both sidebands, plus you pull out the carrier. That saves you a lot of power. When you run single sideband, you pull out 1/2, one or the other, and the carrier, and so it's more efficient by just sending one of the sidebands. Okay, so that's the basic difference. And then when you get into the detection circuits, I'll show you how it can be quite a bit simpler. Or there are different ways of doing it, but an AM detector is quite a bit different than a sideband detector, just because of some of the little circuitry you can use. So, but the reason I got into that is because we're going to actually, the little signal generator that we have is going to be able to generate 2 different frequencies. Okay, one for transmitting, one for receiving, and they're not going to be the same because of the IF thing that I've got going here. So let's say we're on 7 megahertz. Okay, we're transmitting at 7 megahertz. So the transmitter is going to be right at that frequency, right at 7. But what's the receive frequency going to be? Okay, well, if you're coming in at 7 megahertz, and they have to add up to be 11 megahertz out here, that means this has to be set to 4, right? Or else yeah. Well, you can add or subtract them, but okay. So we'll just say this is going to be set to 4. Okay. Now, so I'm going to be able to switch back and forth when you flip the transmitter switch. Okay, from transmit to receive. This little signal generator I have is going to feed to the other transmitter as well. So you've got to be able to flip between 4 megahertz and 7 megahertz. Okay. And then as you tune it, if you go up a little bit on the transmitter side, what's going to happen to this one? It's going to go down, right? Because they have to add up to 11 again, right? So you see the problem that my little signal generator was not set up to do that. It was set up for a single frequency, and you just tune it, it went up or down, but not both. It didn't have the capability to do both. So I'm having to put quite a bit different circuitry in the, not circuitry, quite a bit different code in the PIC to be able to handle both of those frequencies and to be able to switch back and forth. And so with the tune, you're actually changing both frequencies simultaneously and generating all the parameters so that the SI570 will talk on both of those frequencies. After this is all pretty much right from the Retro 75 by Dave Benson. But here's where the difference comes. On the right side. Now, it feeds from the filter right into a cascode. They call it a cascode. It's an IF amplifier. And this is Dave's design again. But then coming out of it, Dave had a real simple detector for AM. And I couldn't find, I was trying to find it here quickly because, you know, this is not the one I wanted either. Oh, I'm sorry. Anyway, he had a simple little, I'll draw it on the board.
Do you know what the name of the file is?
No.
Oh.
Basically, if you ever did a crystal radio, okay, what you're trying to do is very, very simple. You're trying to get, when you're doing an AM detector, you're trying to filter off all the fast stuff, okay, and just keep the real slow stuff. So you have basically a diode, okay, and basically you want only half of that too, okay. So you have a diode, and you have a capacitor to ground, and then you basically have a resistor to have it blown through. Okay, so the simplest idea for an AM detector is like this. And Dave did it in his original SW with he had a little MOSFET up here, bias near cutoff, and he said I always wanted to do one like that, so I did it, and it worked basically. But it wasn't strong enough. It wasn't good enough to really do it, and that's one of the he said was one of the biggest deficiencies in his receiver. It wasn't sensitive enough. And it was because of this little detector wasn't good enough. So he suggested I go to some kind of an op-amp detector. And so that's what this one is. It's not an original design of mine. I mean, I've got ideas from different places, and basically it takes a very high-speed op-amp. This out here, this one, and these two are, this one's an AD826. They're two to apart, so it takes two of them to get three of them. And they're not terribly cheap. They're about $6 or $8 a piece, but that's not terrible. And but they have to be fast. They can't be the normal run-of-the-mill op amps that we use for so many of our circuits. But basically, it's just a little detector circuit, and you get this is taking the top and it's not taking just the top, but it's taking the top and the bottom and adding them together. And that's why you get a nice solid detector out of it. And these op amps are fast enough to be able to handle that whole thing. So it's a real simple little detector, but it's a little more complicated than Dave's original. And then this back end is just his audio. This is an audio amplifier, and this is some feedback circuitry for his mute and audio level control. And then just turn it on. This is the mute circuit. So, but basically just an LM386 for an audio amp. That's it. It's a real simple little receiver. I'm in the process of prototyping it right now, and I said I got hung up on the software. So I didn't get it finished, but I'll pass around a picture of what the receiver is going to look like. And let's see, there was one other piece here I was going to show you. Oh, let me back up 1 second. When I was developing this, I started reading some things about it and said, hey, there's a neat way to make a real simple sideband receiver, not AM but sideband, that's just about like this. Now, this was kind of like you saw the same thing coming in here, the same low-pass filter and transformer and mixer. Now, I don't have to divide by 4 because this is going to be just for, this is for 40 meters, and I can feed this one directly. But you see all this is a mixer and an amplifier, okay? You mix the two frequencies together and you take the sum and difference and you come up with audio. And you put it through an audio amplifier, and that's a sideband, complete sideband receiver. And that's what I've been prototyping here. I've got this, I'm just ready to try it now. I haven't finished hooking up the input circuit, but that's all it takes to make a sideband rig. And so basically, what the AM receiver I have, it's just going to be putting a little bit more circuitry right in here, and that's basically the same thing. And it'll detect it in a different way. Instead of just the difference of direct conversion receiver like this, it'll be the amplitude modulation through those op amps detecting it. So basically that's where we're going right now. I wish I had more of the prototype done, but that's the way it is, and we're going to have to take it a step at a time. But the other thing about this, by the way, is I'd like to make it kind of interactive. A lot of people have expertise in this, not just us that have played with it some, but we're going to try to pool our resources and have everybody contributing. So hopefully it'll be a fun project. I don't know if we're going to end up making a complete print circuit board for it, if we'll do it Manhattan style like some of these, or what we'll do. We'll have to see how it goes. We don't want to make it too tough, but it'll keep the cost down too if we can go with a Manhattan style if it's simple enough. And there's something kind of magical about having a simple little Manhattan style receiver, so we'll see about that.
Any challenges with designing the filters for this? Obviously, you have a low pass and a band pass, probably.
Those are real simple little filters. I'm not sure if we're going to have an AM to lock out. I'm just a low pass filter right now, but we might have to have something to lock out the band, the AM broadcast band. If that comes leaking through, we're going to have to put a filter trap in there. And I'm not sure yet. That's one of the things the prototype's going to tell us.
Got to get the receiver up to see.
Got to get the receiver up to. By the way, I like this thing with this tuner. I can tune right down to the AM band. I'm going to check out this receiver by tuning in the AM stations on the broadcast band. Okay, with this tuner, I can do that. I can drop it right down to 0 and walk through there close. You know, you can drop pretty low. So it's going to be fun to play with that and to check it out, and then we can move up to our band. And talk, and then we'll be able to compare it to the Retro 75 and see how that one works. Basically, I've heard stations on it, but it's not very sensitive, and it'll be fun to see how this new one compares to it. If we get more stations, and hopefully the goal, by the way, is to be able to talk around the Twin Cities, at least among our club members, to make something that we can chat with and just have fun with. If we get further out, that's great. Put amplifiers on, we can get further, I'm sure. But the first goal is to be able to talk amongst ourselves and see how this whole mechanism works before we try to do DX with it.
Is your goal a kit, or is your goal just
no,
a project?
I don't think it'll probably be a pile of parts. Okay, I'm not sure that we're going to actually offer it as a kit. I'm not sure it'll go any place further than this club. I'm not expecting that. I don't think Dave would really object if we wanted to do it as a club and teach other people how to do it. That's very possible. So, yes.
Do you have a supply of those kits from Dave for the club?
No, they don't have. He doesn't make them anymore. They're gone. That's why I had to buy this one off eBay, a broken one, and play with it. So they're not available. And
it was a pretty limited run. There's a lot of early adopters, so I got it before it was advertised. But I think you're probably talking in the neighborhood of a few hundred on the market. I think the number is relatively small.
He supported it in a Yahoo group for a while, and he also had in the AM group. There's a bunch of people were talking about, made all kinds of modifications and experiments with it, and yes, and good and bad. And Dave told me he had one of the big old AMers out in the East Coast here. Told him it sounded like crap. So he said, "Thank you very much," you know, and so on. So it's not. He knew there were limitations, and part of the reason he got it, he said, "Hey, this is a low end. This is an easy thing for people to understand. It's not the end of the world. It's not the best transceiver you've ever seen in the world. This is for simplicity and for understanding how it works." That's exactly what our club is doing. Okay. That's what we want to do. We want to talk about how AM works, how it compares to sideband, and do some circuits that make it work. Now I'm going to introduce Mert, but before I do that, today's his birthday. Hey!
Mert's 45!
Happy birthday to you. Happy birthday, dear Mert. Happy birthday to you. Well, you got to go too high, Mert.
Very glad to be here. Very glad to be here. Craig and I have been working pretty much separately so far, and as you can kind of imagine, we're going to have to start getting together because some of the things that I've done will kind of overlap into what he's done. We've got to decide how this is all going to fit together. But I've been working with the RF end of it, and let me give me your plug over there. I'll
You want
plug
to
in
go right from there? Okay.
Yeah, I'll work from here.
Okay.
I think. What's the matter here?
Upside down?
I don't know. Upside down, no? Can't tell which end is up. I guess I was upside down. still isn't making it. Apparently, or do I have to push the button over here? How does that go again?
It's probably a
F,
function F5 or
F7.
F6 or something like
F7,
that.
I think it is. Whoops.
We tried several before I got a blue scooter death on mine a little while ago and had to reboot it. So
Oh, it's coming. Isn't it?
looks like I pushed it too many times. I think. Good for you. You got it.
Okay. Let me get the right picture up there.
Why don't you tell me what your background in transformers?
Okay, there's the, here's what I've done so far with the RF. In order to do some experimenting, I've got a crystal oscillator on the left-hand side there. As you can see here, I'll use my pointer. Here's the crystal oscillator using a J310. It's a conventional Colpitts oscillator with a crystal in it. I put a little capacitor so I can pull it the frequency a little bit if we want to. But I've got to interface this to his SC570, so this won't be there. Okay, here's a buffer driver that we'll probably use. It's a emitter follower, so it has a fairly good high input impedance. It's got a low output impedance, and I've put an adjustment on it. We may or may not need that adjustment, but for experimenting, I needed the adjustment to vary drive and see how things are happening.
Is that just a basic NPN that you're putting behind it, or what are you using for a buffer?
That's the buffer right there.
3904 NPN, yeah.
3904, that'll work.
Yeah.
They're similar. Okay, that's coupled. I've got a blocking capacitor. I take the DC out, but it's coupled to a transformer that's a little toroid, FT3761 with some proper turns on it to get impedance here that'll be able to handle, like somebody said before, the input impedance is going to be would probably be about 4 times what the resistance value is here. Anyway, that couples to here so that I can get a plus phase and a minus phase out of it, a center tap transformer, so I can get a plus phase and a minus phase to drive the push-pull final. See, this is reminiscent of what used to be push-pull vacuum tubes for the final amplifier. I had FET transistors in there in an earlier model. I tried that; it works good, but I didn't like it as well as I like this model here. Now, I show a 3904 in there. That's just because my simulator had that in it. I'm using some other transistors that I found that work good. I got a couple of different choices. In fact, this push-pull final is very similar to what Diz, W8DIZ, Diz has on his 40-meter transmitter that the guys are talking about on QRPL right now. They're building them and they're using them. This push-pull final is very similar to that, and it has similar transistor usage. Okay, here's the problem. Right here, we can get RF out, and our RF that we get out of the carrier, is going to look like. The carrier is here, at this height. When you do 100% modulation, the modulator blows it up to twice height and subtracts it down to 0. Okay? So the carrier sits here, but when you modulate, it does this. So the instantaneous peak power on 100% modulation is up here at twice voltage, so that means 4 times power. So that the final has to be capable of an instantaneous 4 times power to hit that peak. And we got to subtract, and it's got to be fairly linear then all the way,
So what kind of voltage are you talking?
Okay, this voltage, the voltage I'm talking about on the final is a 12-volt supply.
So you have to be able to have 60 volts or better then.
No, here it is. Here's the final. It's 12-volt supply here. This couples to the audio amplifier, which I'll show you in a minute. The audio has to give us a plus, go above the 12 to 24, and minus 12 down to 0. So in effect right here, we've got to have an audio swing from 0 up to 12. So the bottom of that picture is 0 and the top is 24 as far as that voltage is concerned there. So that's how you get your 100% modulation. This is high level modulation, and it takes that. The thing that makes it kind of difficult, and I hadn't really thought about it too much before, is here's the transformer that's going to couple the audio signal and produce that variation in effective DC that gets to the final. This transformer then has got a handle that's going to be DC going through this winding to supply the RF amplifier. That DC in that winding produces a lot of magnetism that shifts the whole operating thing over. Here's a picture of what a transformer does internally. This is the BH loop, or the BH curve for the transformer. A normal transformer, see, we put a, and this is like the input drive H, the magnetizing force H that we're driving the primary with. And this is the flux that's being produced in the core. And that flux is what links the secondary and produces the secondary voltage. So that this in effect shows the input and output of this transformer. Now on a power transformer, we've got this whole thing here to work with. And we put, like, for a primary side of 115 volts, we swing the thing 115 volts. 115, now that's the RMS value. So if you think of what that's doing, the peak value of that thing's going to go to 160 volts here. 160 plus, 160 minus. So the windings on a transformer primary have to be such that it'll swing that thing all the way to make full use of the core. That's why we have to have so many turns on the transformer to make a primary. You got to have enough turns so that when you apply the voltage, it doesn't drop too much current and swing it up to where it starts saturating. And saturation will cause too much current to be sucked at the peaks, and too much current means too much loss and heating, and you may burn the winding out actually. So then a power transformer running all the way. Okay, now if you reduce the voltage on the primary down to here, now we're swinging on this curve in this region. Now we've got some room so that we could put some DC in there along with it and swing the operating point over to here. And at that point, see, we're over so far that this peak here is up in the saturation region. And that's what we're likely to have in the modulation transformer. We've got a lot of DC in there. We've got to have a transformer that so that we can set the operating point maybe someplace in here with the DC that it takes, and have a swing like this, and it'll still be on the straight portion of this curve. Okay, that's basically the problem. So here's the modulation transformer again, but with the audio amplifiers ahead of it. Over on this side is where the microphone preamp feeds in the signal. And I made a little homemade microphone with a little preamp in it. It's got a little electret microphone in it. I put in a push to talk switch too, so that we can turn it on and off. But there's a little 741 op amp in there doing the preamp stuff. We can put something in the box to get some preamp so that we get maybe 50 millivolts or so over here. to drive the first stage of audio amplification, I found that I had a little too much high frequency response, so I put a little capacitor from here to lob off the high end a little bit. In fact, in some of my earlier work, I had I also tried MOSFETs out here. I tried the 2N7000. It worked good too, but you know they had so darn much response that it would oscillate at RF if I wasn't careful. So that's one reason it prompted me into cutting back the gain on the front end here, cutting the high frequency off so it wouldn't oscillate. Anyway, that's the preamp, or that's the amplifier following the mic preamp. And this stage here is a phase inversion stage to get the push-pull. Again, we're talking about a push-pull amplifier for the audio. And one reason why we're talking about it is because using push-pull, you get current going through the transformer in this direction on one half cycle, current going through the other in the other half cycle, which cancels the DC, so the DC magnetization is zero. So that for this transformer, for the transformer part of this, for the audio transformer, we're doing this. But we've got to somehow put enough design into that transformer so that when we run the DC through the secondary to go to the RF, it doesn't pull that thing way over and saturate it. So one way to do it is to look at the transformer design, which has to do with an EI lamination used for the magnetic core of the transformer. I brought along a couple of little E's and I's if you want to look at it, but there's a picture up there showing an E with an I. That I would normally be butted up against there tight, so that the magnetic path around there would be good. The coil is wound on the center leg. When current passes through the coil, it magnetizes the center leg, and the magnetization flux comes out this way and goes around. And it's split, at this point it's split. See, half of it goes in the outer leg, the other half goes in the center leg. So you notice the outer legs are half the size of the center, so that half the area of return flux is here, and the other half of return flux is here, so that you've got flux on both sides for that transformer. Now, in order to make the transformer not saturate with DC in it, one way to do it is open up a gap right in here to make the magnetic path not so good, so that the DC magnetization force can't really push it to saturation anymore. Now, we really want the winding to have a certain impedance, and like the gentleman back there said earlier, we need like about 4 times the input impedance of what we're going to use in order to not affect the input characteristics. So we've got to have, I got to doing some calculations, and I figured I needed about 100 millihenries here to get the inductance I need. And so I've got to design a transformer that I can stack like this with a bunch of air in it and still have enough inductance to produce 100 millihenries. So that was basically the problem. To go from a really good transformer to a kind of a lousy transformer, but still good enough to operate. And that's basically what we're talking about. So I've got, here's what I used to, showed you the pieces. I found places to buy lamination. I had a whole bunch in my junk box, so I was able to put together some prototypes because I used to be in a transformer business at one time. So I had a bunch of this stuff. I thought I got rid of it, but I got to looking around, and I found that I had a few boxes of junk with laminations in it, and bobbins to wind the coil, and got some magnet wire, which is nice ductile copper with a good enamel film insulation on it, so I could wind up some transformers to do the job. So I did it, and I made some breadboards of the audio amplifier and also the RF amplifier, which I've got here. And I've done some testing already, and I've got a new one in there now that I haven't really tested yet. So I'm getting to the point where I think I've got a good transformer that'll probably do the job, and I've got a pretty good 2.5 watt amplifier. My goal was to have a carrier that would be about 2.5 watts, so that the peak would go to 100 watts peak envelope power.
100?
Right up here,
not
when I
100,
go to double voltage, it's up at the peak envelope power.
5, you mean? Not 100 watts, right?
Excuse me?
You said 100 watts?
Oh. Okay. Excuse me. Why, you're gonna kick me out of the KSP club, I can see that. Okay, 10 watts, 2.5 up to 10.
That's right.
Okay, my mouth moves faster than my brain. Okay, so that's basically where we are.
How many windings are you talking about on here? How many turns do you have?
Okay,
so far?
I'm in a 200 turn neighborhood, so it's not too bad.
He's got a winding machine to do this, by the way. A little electric
I got
motor.
a little.
I thought you were going to say his wife.
No. He's got a machine to do it that he used in his business. So we're going to be able to take that and do it here as a club.
You can get a little universal motor with a sewing machine, rheostat on it, you know, so you can.
With a counter, though.
You have to have a little chuck on the shaft so that you can chuck in different bobbin holders and stuff. But and the main thing is a counter, because you want to be able to rev that thing up to 400 RPM, and the counter will keep track of the turns for you.
And then you feed it back and forth, so
the
it's
turn
spread it out. And he showed me how to do it.
It's not too bad. 200 turns isn't that bad. See, because consider a transformer that size, that if you're going to put it on 115 volts for a power transformer, the primary would have to have like 4 times, it'd like to have about 16 turns per volt. So see, it'd be 16 times 100, so you're up around 1,600, 2,000 turns in order to just get a primary on there. So this isn't so bad. The 100 millihenry, the 100 millihenry is based on having a 300 hertz bottom end of the audio. I'm figuring 300 to 3,500 as the audio.
Human voice.
So with the 300 hertz will be about the bottom. Now I found that my inductance meters weren't doing me too much good, and so I rigged a 60 cycle. I did a variac and a isolation transformer and step down isolation, so I could drive that 200 turn winding and see where is it going on that pH curve. And I ran across an interesting thing when I was doing it. I got an unusual effect, and I thought, whoa, what's that? When I put all the I's, you take all the E's, and then you put all the I's on there. Well, I needed something to hold those I's, so I put on each end, I put an E in reverse to hold it, so that the end lamination, see, was across the gap, you might say. So when I fired that up, I got, ooh, I got a bump in there, and I thought, where the heck is that coming from? And so I had to realize that, hey, when I started turning it up, it first has to saturate that little bit of iron on each side before it takes it into the part that's governed by the air gap. But yeah, it scared me at first until I realized what was happening. No, that transformer then, see, I've got an audio amplifier here, and Craig's got an audio amplifier. So somewhere along the line we're going to have to merge, because, see, I think if he needs audio amplification, he can just switch it over to here. I've got plenty of gain here. And I've got a transformer on there that I can tap to match a loudspeaker. So I think maybe after we talk it over a bit, it'll end up that we'll have this, so when you switch over to receive, we use my audio amplifier and loudspeaker system, because we've already got that, and it'll be be 1.5 watts. That's like Craig said, when we're modulating 100%, we've got to furnish half the carrier power in both sidebands. So it means we're going to have, if we have a 2.5 watt carrier, we're going to have 1 1/4 split in half. So we'll have to have like 600 milliwatts or so audio to do it. So
how low of an audio frequency do you plan to use?
300.
300 hertz. Oh, okay.
Yeah.
You can see, by the way, the little transformer he had in here. This is the transformer he used in the retro. That was way too small. That's why it was getting saturated. Merc explained exactly why. You need a little bigger one. If he would have beefed this up, he would have had a more. He would have gotten the modulation that he needed out of it. He knew that was a limitation, and he needed bigger. And Mert knows how to do that.
Was that a function of Dave trying to take commercially available parts?
Trying to
that
make
you
it
buy
small.
From someone, yeah.
Trying to just make it small, and he didn't realize how big one. He didn't realize that effect of the DC going through it all the time, like Mert was explaining, saturating it, and then he didn't get the fluctuation on top of it that he needed.
The transformers in the old CB rigs used to be about the size of $0.50.
Well, yeah.
They were, and that was for 5 watts, and they were pretty good size.
Yeah, this is just very typical of the old plate modulated type.
Exactly.
Yeah.
The old tube stuff.
You bet.
Yeah.
How hard is it going to be to source the parts to make transformers like that?
Mert found
Well,
out.
I didn't really, I didn't really, at first I didn't really think about us doing it, but Craig thinks, hey, that might be fun, so I don't know, you want to build transformers? We can build transformers.
I mean, is it something where you
He
can
found a place to get them. Yeah,
I
he can
found
buy
a
all the
place,
cores and the bobbins and everything.
I found a do-it-yourself place. I think it's for audio amplifier people, where they sell the laminations and of sizes that'll work for us. And I know where I can get bobbins and magnet wire, of course, we can get. The channel frame that holds the thing together, I think I can get from the same place where I get the bobbins. Transformer supply houses sell this stuff already made. So you get the channel frame and the bobbin, spool of wire. I mean, we could probably design so we can use one size wire. It may not be perfect, but it'll be okay. Or maybe 2 sizes, I don't know.
I would highly recommend that the reactions on your modulation transformer be high enough to get down to about 250 to 200 hertz, because the voice sounds so much nicer.
You get a little bit more bass.
Because that's what AM is, It's
Yeah.
just like WCCO.
Yes.
Yeah.
The old
You want to go? You want to go lower?
Right, go lower.
Yeah.
Go down
Well,
about
to
200
go
hertz.
lower, we got to have more inductance,
Right, of
which
course.
means either probably a little bigger transformer,
Right. I know that's.
or at least I have to make sure I adjust
you
my
can-
design
if you
so
got
it will go lower.
But if you got the cord, and it looks like you can do it.
Well,
you
this thing doesn't just jump down though. I'm saying 300 is my design point for the low end, but it'll still go, but it's
Or-
reduced.
Or if you're on a
It
downward
doesn't-
slope,
it
maybe
doesn't
you can
just
do
drop
some
off.
Equalization too. In the audio, just do a little bump to where you can at least get it down to
Yeah.
250 to
It goes down at maybe 3 dB per octave, like a regular roll-off,
Right.
a regular inductive roll-off. As the inductance gets lower, it gets lower like.
That'll be fun though, to experiment with.
Right. Yeah.
So,
It'd be interesting.
The voice sounds really natural. I mean,
Yeah.
you see what these guys have done on 80 meters on both sides.
Yeah.
Yep.
But I suppose if you want to have something that really sounds good, we want to
Make it bigger. Yeah.
one size
Yeah.
bigger. One size bigger isn't that big either.
Yeah.
This is, excuse me, this is one size bigger right here than what I've got in there. I've got a so-called half-inch transformer there, and this is a 5/8 incher. So
There is an excellent also. There's some really nice. It's a 2216 chip that does audio processing, and it does. If you put a microphone into it, it will do your compression, it will do your limiting, and it will be a noise gate at the same time.
well,
It's
maybe
a
I.
fabulous little chip for your microphone use. And you can put that
Maybe
in
that'd be a
your
front
audio
end that we could use.
Maybe our goal should be for
Because you got to do some audio processing with AM.
Yeah.
You just can't run it raw. You'll get a clip and you can
So what kind of chip is it? How many pins are you talking?
2216. It comes in an SO8,
Okay.
but you can get one of these little conversion guys where you can solder it onto a little pad that then sticks into
A dip socket?
8-pin dip.
Okay. 2216, huh?
2216, yeah.
Oh, look
It's
at
an
that.
SSM 2216, I believe it is.
SSM. Okay.
Yeah, because I got some. I'm gonna put it in my transceiver, and I just got some. So
Okay.
it's very simple. You can do if you do your compression on like having been in broadcast engineering.
Oh, really? Oh, you know all about this.
The voice sounds really nice if you most of these people use go to an 8-to-1 compression ratio.
Yeah.
If the audio input goes up 8 dB, the output only goes up 1 dB.
Yeah.
But really, the voice sounds so good if you just keep it at a 2-to-1 compression ratio. Wherever if it goes up 2 dB, it only goes up 1 dB, and let it slide for you can do about 20 dB of compression. That will,
Wow. We
and
can
then
monkey
do
with a
some
lot of
very
this.
soft limiting on top of that, and the voice will sound very, very, very nice.
We're going to make some nice sounds. That's interesting that you have that background too. This is all part of the project to make it, variety of different ways
Well,
and
it's a
different
nice
modifications.
It's a very old conventional.
It is, but why
plate
not?
modulation.
But why not get to know about how it works? That's
Sure.
exactly what this club is about. So,
How much are they?
Any idea what the part cost?
I think I got them at DigiKey or Mauser for about $1.87.
okay, good.
Yeah, and they're really nice. I mean, they'll take a microphone in, put a left track.
Yeah, that's what he built here, right?
Are you on AM on HF bands?
Not yet.
How much
I do have some
DC
nice
current
audio
are you talking
processing
about?
that's in the rack waiting.
How much what?
How much DC current is going?
Oh, it's 300-400 MA to the output.
You're talking about 3 or 4 milliamps? That's causing you a problem?
100, I mean. Excuse me.
Oh.
Okay.
Excuse me.
There is another
No, I figure well, it'd probably be closer to half an amp actually, because you figure you're running 2.5 watts and you maybe got 60-70% efficiency. So you figure that out with 12 volt supply, you end up in a 500 milliamp range. I'm set up here now. I got a board with the audio amp and the RF amp on it, with a antenna changeover relay. And I was gonna try it, see if I could get it on the air and see if Craig could hear me over at his place one of these days. So I'm goal is to set up so I can check it actually on the air and see how it works. I don't have the output filter on here. I've got one on I had another breadboard for my first attempt, and it's got the filter. I'll put the filter over here and finish this off and be able to test it on the air.
What class are you running your finals in right now?
It's a class C in the class C, a wide C in the RF, and it's like AB in the audio.
Yeah. Okay. You don't need full A. A would be perfectly linear, but AB is close enough for audio. That's typically what the red and ham.
Oh, say because I'll show you. Look, what the hell's happening here? It's responding. Huh? Why isn't it responding?
There you are.
There we go. See here's the final error. See, to make it A, they bleed in a little base current by that pad. See these pull-up resistors here, they're like 100K. To bleed in enough current to get those into conduction a little bit, to take me into the bottom of the A range. Then the signal will boost it on up after that. But it's not right at the, for class B it should be right at the cutoff point so that each half goes in, one half goes in and then the other half goes in. They change over like about 0. Well, these cross over, you know, a little bit above zero. So there is some standing current there. So the first little bit looks pretty good, and then you do hit a little bit of a bump when you're putting in a sine wave, that is. When it's real low level, it looks really good, and then you can kind of see the crossovers coming. You can see a little bump, and then as you go on up, then it takes over, and you get the sine wave on up. So there is a little bit of a bump, but not too much. Of course, in the Class C final, you don't really care because you're filtering that thing afterwards anyway. In fact, I'd like to be able to bang that baby square wave. I'd like to be able to hit it, and it probably will for full output. It'll be hitting the top and the bottom, so it's like a square wave. That's ideal. What I'd really like to, and I talked about that with Craig over lunch today, I'd really like to have a pulse width that's about 90 degrees. Not the full 180, but about 90 degrees, and go all the way up, bang, and all the way bang negative. So, and that's what you put into the output filter, so that you got a good rugged fundamental that you filter to get the sinusoidal into the 50 ohm load.
And we can do that with a signal generator by using an op amp with some limiting on the top and bottom to change the width of those pulses, so it's not driven strictly at 90 degrees.
Right now, some of my testing now, I didn't have the filter on there, and I put the load right across here, and it wasn't too bad a sine wave right there, because it was putting in, you know, it was operating on their Class B, see. But my drive is a little limited. I've got to work on it. I'd like to be hitting that a little harder yet. It works, but efficiency isn't too bad, but I'd like to improve on it a bit. It might be just a little better adjustment of the drive transformer here, so I could get a little better drive match and get that extra out of it.
What Mert's talking about is pretty magical, though, when you're trying to figure out, you know, how much drive you need into your finals to try to get the sine wave that you're looking for, and it's a tricky process to get those dialed in. You know, trying to figure out how much bias you need to get them to open up.
Yeah.
So we're going to keep doing updates like this, by the way. Probably each club meeting, we won't be doing the whole meeting, but a few minutes maybe to tell where we are and explain things and get some feedback, and we're going to be doing. It's going to take us a while to finish it, get the prototypes working, but we're making progress, and I think we're going to have fun. So yes.
If that doesn't work out, another way you can go another direction, which is, you know, I'm not recommending this per se, but you can use like two 3904 transistors and tie the emitters together, one resistor to ground, and you put your RF in one side, and of course you got collect resistors too, and your audio in the other, and you'll do low level modulation. Like you're only going to be putting out, you know, 10, 20 milliwatts.
Yeah.
You can go with low level modulation and then go through an RF linear amplifier course and then start boosting that up to get your.
Yeah, we've thought some of that too. Yeah, there's low level modulation that is pretty typical, and that's what quite a few people are doing. And we thought of it, but then we thought, maybe we go back to the old.
Yeah, well, this might actually be a.
See if we can resurrect the old system.
And part of the fun of it is actually make. I don't know how many people have made transformers before. I've never done it, and I really want to do it. Okay, and I think we can make a real fun thing out of it and show. You know, this is a real basic mode of operation. We're into basic things, right? CW and how things work. Well, this is how transformers work, and one of the basic functions of what they do.